So hope everyone's having a good afternoon. Today's talk is going to be on data architecture. Now, this talk is going to be not necessarily like revolutionizing, that's the ChatGPT thing. It's going to be providing some insights or some tips for how you can design your operational data to make secondary analysis, or let's say input to AI, easier. So with that, let's get started by defining what we mean when we say operational versus secondary. And these are my terms, not really industry standard at all. But operational data is pretty much anything that's crucial data storage for business operations. We'll talk through some business use cases of what operational data versus secondary data would look like. Typically, this is going to be heavy user input from your end users, or maybe your client services team, whatever. It's the main system of record, and there's requirements of high availability and high read and write throughput, so you're not losing any data. And it's going to be something that is central to your operation, depending on what your business is. Whereas secondary data is any data derived or replicated from operational data. Now, that means that if I write something to my system of record and then I read it to some other data source, now that data source can now analyze that, transform it, do whatever it needs to without affecting the operational arm of the business. It doesn't mean that you can't use this secondary data from the operational arm of the business. It just means that it's not affecting the operational data. And if the analysis engine goes down, I'm not incapable of conducting day-to-day business operations. Data input for secondary data is typically handled by automated process, aka ETL, which we'll talk about later. And like I mentioned, you can run analytics, aggregation, reporting, do a lot of different things based on that input data without disrupting your data flow. So I'm going to come up with some sample business cases. These are very contrived examples. So just for this talk, they're going to be different, but I'm going to be referring to them a few times during this reporting aspect. So the first one is your typical e-commerce site. Just talking about, let's say you have a microservices, or maybe just like a single source of truth data system. You're going to have domain objects like products, customers, and orders. Your operational data workflows here are going to be to manage the products. You might have a marketing team that decides to update names, descriptions, product images. You might change your prices based on market forces. It's going to be responsible for creating orders and customers during the checkout process. So like an Amazon thing, every time I click submit or I create a new order, I need that order to be dumped to my inventory management system and eventually to ship to me. And then you're going to need to integrate with payment and shipping vendors. So all of that data is going to be stored in your operational data center, or your operational data storage, whatever that storage might be. Your secondary data workflows, these will inform the business decisions that get made about, let's say we need to ramp up marketing of a specific product or a specific time of year. Calculating reporting total revenue, for instance, how many quantity, how many product count have I sold of a specific SKU so far. You can drive deeper analytics into conversion. For instance, when we ran a coupon code improving 20, did that increase the amount of sales we got over a specific period of time that coupon code was active? And you can also identify trends in product purchases by location or by date. You can slice that data up. And the point is you can aggregate that without affecting someone else making a purchase. So that's kind of the difference we're talking about. We're talking about operational versus secondary data. There's also an inventory management system. So the operational data flows for an inventory management system might be ingest products from wholesale shipments from suppliers, inform your external systems of current stock. So if someone were to go to my e-commerce site and say, hey, can I buy this? You wouldn't say, oh, we're out of stock on that. Handling over and underflows in stocks. We ran out of something we can't ship anymore, or we got more of something than we thought we have more to ship. You can also plan and track outgoing shipments to other parties. These are all core business functions, like day-to-day business functions, but they're not driven by analytics. Secondary data workflows, for example, might be detect anomalies, excessive spoilage, or maybe a specific SKU is taking a long time to ship from A to B for whatever reason. Maybe there's not enough refrigerated trucks, so we need to try and increase our number of refrigerated trucks in our fleet. These are just example analytics or insights you can pull from it. You can automate the end of day, month total inventory counts. So let's say I have an automated process that runs, just crunches through all of the inventory changes that have happened over the day and reports that number. So you can see at any time at the end of the day or at the end of the month, here's how much of each SKU we have in each warehouse. And you can also track trends in outgoing stock. These are just sample analytics. And then of course, one that's near and dear to me is a custom baseball statistical tracking system. So some of the operational data workflows might be handle registration and rosters, track live and historical scores or standings, schedule games based on availability. That's going to affect the day-to-day operation of how the baseball league runs. But if anyone's here is into MLB, you can also use that to calculate individual stats to see who's leading the league in average or ERA. You can summarize a player's performance with sabermetrics, and you can do some other fun stuff as well with that. So those are just some sample business cases that I'm going to be referring to, but that's the whole goal of that is to give you some intuition on what would be considered operational, what would be considered secondary. Okay, so we can move into operational data design tips. The idea is for all of this is to make it easier to aggregate and analyze later. The better your input data in general, the more analytic value you can derive from it. So the first tip is going to be something that intuitively makes sense. Keep your stored data atomic and granular. Now, I don't mean atomic in terms of like an ACID transaction. I mean to determine a lowest level of data to be collected. Because, and we'll go through an example, but it's always possible to aggregate like multiple child records into a like grouped record, but it's almost impossible to go the other way around. So as long as you need to be capturing as granular data as you can, and you can derive as many insights as you can off of that. So as an example, and give some extra credit for anyone who can recognize a specific situation, unless you're from Houston, in which case your vote doesn't count here. Let's say we have that MLB statistical analysis thing that I was talking about. And maybe a naive implementation would be, okay, I'm going to store each at-bat. So this particular at-bat happened in the top of the ninth between Adolis Garcia and some guy from Houston. And the result of the at-bat was a home run, and he hit 4 RBIs, making it a grand slam. Now that accomplishes our goal of tracking our scoring and tracking what happens during a game, but we have no idea of how to get any kind of advanced analytics from it. Instead, what we could do, just as a sample, is keep that same at-bat structure, but also start tracking each pitch as it comes in. This particular home run happened on the third pitch. It was a 97-mile-an-hour four-seam fastball. And it was a little bit off the plate, but right in the middle vertically. And he absolutely crushed it, hit 110 miles an hour. So the point is, it's very easy to aggregate this pitch data into an at-bat result. It's almost impossible to try and figure out what happened per pitch if all you're starting from is just an at-bat. That's what I mean when I say atomic and granular. Another key is to try and capture the 5 questions around a state change to your system. The who, what, when, where, and probably the most importantly is why. So when inspecting your data independently, we need to be able to track the rationale behind a change. In general, there's this concept from Michael Perry, who works for Improving, called historical modeling. And it says that the change matters more than the state. So we'll go through an example of what I mean by changes later, but the intent of a circumstance the intent and circumstance of a change matter more than what is being changed. In general, if I'm trying to reconstruct back in history, let's go back like 2 months into my data, and I'm not capturing why something happened, it's going to be almost impossible to try and interpret why something happened. But if you start to capture the reasoning and the who, what, when, where, why around a change, you can start to gather insights that, actionable insights from that data. So as an example of that, let's consider the inventory management system. Now on the left, we have another somewhat naive implementation where there's an inventory transaction. We get, on the first of June, we added 500 units of this particular SKU. On the 2nd, we removed 200 units. On the 5th, we removed another 100 units, and on the 5th, we also removed another 200 units. Now, the end result of this is going to be, if we're taking it as a ledger, the end result of this is going to be that as the end of the day of the 5th, we have 0 units of prod 001 in our warehouse. That's our operational data. We don't have anything to sell of that. But if we're trying to figure out why that happened, or we're trying to figure out, did we under or overstock something, it's almost impossible to try to figure that out. So if we start to capture some more rationality behind it, for instance, if we just include a reason and a note, for instance, product received from the shipment, that product was received as a part of like a vendor's purchase order 1. Product destroyed via malfunction. Let's say someone drove a forklift into pallet and just completely obliterated some product. So we lost 200 units of that. Maybe it expired on the 5th, so we had to lose 100 of them. And then finally, we actually did end up selling or sending or transferring 200 units. Now, from an operational perspective, or from an analysis perspective, I would actually care more about the expiration. I would say, like, okay, how often are we having these hardware malfunctions? How often are we having to deal with expired produce or expired product? These are the kind of insights that you can derive when you start to capture this data. Another concept is avoiding destructive data changes. So in-place updates and deletes can mangle your history, making point-in-time recovery of data difficult or impossible. So as an example, let's consider that products list we had, and let's say I just have a product and a price. And as I'm changing that price, I'm making changes to that price based on market forces. If I change it and I don't track what it was historically, let's say on July 1st of 2023, it was $2, and on July 1st of 2024, it was $4, which is probably some actual real inflation there. If I care after July 1st, 2024, what the price was in July of 2023, I no longer can because I've destroyed that data. Some alternatives are you can model changes as the children of a root object, or store pure events if you're using, say, an event-driven architecture. Now, the drawback to this is that it's going to add a knowledge hurdle for the development of those operational features. So if I have to know that, oh, I have a product, as a developer, I have a product object, and I have 5 price objects in an array. I have to know that I want to pick the most recent one, or the one that has, a start date earlier than today and an end date of null. I need to know that to do that rather than just having a product with a price property. That's what I'm talking about when I say a knowledge hurdle. So an example would be, let's say we have an order from the e-commerce thing, and most of this is modeled as JSON. I don't want anyone to assume that this means that I'm saying to use MongoDB or a document DB. I just find JSON to be pretty descriptive, and this is really just a model and not a storage implementation specific. So for order 123, it was initially submitted. The user purchased it at 1 p.m. on the 1st of June. Then the system confirmed it 5 minutes later. We shipped it the next morning, and then 5 days after that, it was eventually delivered to the end user. Now, when I say update 1, update 2, update 3, you're considering that this is all like just an order date status. Meaning, if I'm executing this query saying, show me the order as of July 1st, 2024, this is all I'm getting. I'm just getting the state of delivered with the date. I don't see any of the history contained with it. So as an alternative, you can model this as children records or children transactions or something to try and track the state as it changed, as it naturally evolved during business operation. So with this, it doesn't matter whether I'm querying this on the 1st of July, 2024 or 10 years later. I know that we confirmed this order 5 minutes later, or we shipped it a day later. We can gather that we have that information, and we can build better actionable insights from it. And in general, when you're designing your operational data, you should be considering the business usage of secondary data. So secondary data can still be used for primary business functionality. If I'm talking about that that inventory management system, I'm still probably going to use that automated process for auditing purposes. I still need to know what's the end of day value, but my inventory transactions that are affected by day-to-day updates that are stored in some SQL database somewhere, those are going to be my operational data, but I'm still going to be relying on aggregating that data to inform the core business. So one of the things for secondary data is we need to figure out both how often we need to process this data and how much data we're taking in to try and figure out how we're going to do this. Now, those use cases can range from, oh, I have this data that doesn't change very often, so I can actually run a process once a month, once a year, maybe, to, oh, I need to continuously be updating this because I need to know the current up-to-date value of stock and inventory. Now that's one of the more strict, one of the more high intensive use cases for data processing, but modern tooling allows us to do that if we need to. But it's one of those things that you need to be almost baking into your initial system architecture when determining that. Okay, so before we move on to secondary data storage, implementation specifics and some examples, I want to clear up some terms that I'm going to be using and are used a lot, like kind of interchangeably. Data lake is just a general term for trying to commingle as much data as possible. In the example of the e-commerce application, let's say I have a products microservice, I have an orders microservice, and I have a CRM tool that handles all of my customer stuff. The concept of a data lake is all of those systems might be in different databases, they might be in different complete networks. But as long as I can dump data from each of those microservices into a central area, I can process that, do any kind of like artificial joining as needed, so I can build those insights. A data warehouse is a general term for the results of an analytics process. I'm going to go through specifically what I mean when I say the result later, but it's just it's just after you transform the data, after you process the data, after you aggregate the data, you're going to be putting it somewhere else. And the whole point of a data warehouse is that aggregating data, especially when you're crunching numbers of, say, 10 million transactions, that's a very expensive process. But if you can do that aggregation, that processing once, and query it 10,000 times after that, and just look at the result, that's exponentially cheaper. And especially since you're not hitting your operational data, which is the whole point of these secondary data flows. And then we're talking about ETL, extract, transform, and load. It's an acronym. It's just a general term for processing that takes data from operational to secondary. That could be as simple as just a script that runs to aggregate, or it could be a direct copy. Like I pull data from products, or I pull data from orders, I load data from products to join it, and I load data from customers to join it, and then I go in and I aggregate it, and I dump it in some data warehouse somewhere. Those are just general terms that are pretty industry standard for how to process data. So I'm going to go through some workflow for sample processing options in terms of ETL. So here's an example from the e-commerce. We have from the orders database, we have order items that have a product ID, a quantity, and a unit price. We have products and some other potential data store that have a name, a description, and a unit price. That's at that point in time. We're going to be extracting this, putting it into a data lake. Now, the whole point of that is so that I can select from multiple data sources in one query without having to, or one process. But in this case, we're talking about a query. So my query in this case is going to be, I'm going to sum the order quantity and sum the unit price by that time, that quantity. I'm going to group by date and product ID. And the whole point of this is when I'm sending it to my data warehouse, the composite key that I get of date and product ID is total quantity and total sales of that product by date. So This is the extract step is putting stuff in the data lake. The transform step is a query that wants to aggregate it, and the load process just moves it into the data warehouse. And the idea being that after this point in time, you can just run a simple select star from data warehouse to give you that aggregated result without having to worry about how that query is written to aggregate it in the first place. And you don't have to re-aggregate that data every time you run the query, just once, and then the query pulls from the destination data. So there's some very simple single database flows. Now this is for, let's say you have a low input e-commerce site. You don't necessarily need some heavy duty Apache data, high data, big data stuff. You just need, I need to aggregate that data. So you can use the tooling included mostly with your DBMS. The general process looks like query with the group by, like I mentioned. You can automate that or run it with scripts. So as an example, this time we are going to use MongoDB. As an example, I have an order date of June 1st, 2024. I have, two products that were included in that order. They bought two of product A and one of product B for the price of $5.99 each, or $10 each, get the total price. And I want my output to be for product on this date for this product. I want to see how many orders came in. I want to see the total item count. And I just want to see the total price. And so this is an example of a script that's run using Mongo's aggregation pipeline. And if you have never worked with Mongo's aggregation pipeline, I would highly recommend taking a look at it because it is very powerful. But it can largely simulate the ETL process entirely. So in this case, I'm wanting to unwind my items because I need to flatten that because order has an items. And then there's the group by stage where I'm going to build my composite key here with the underscore ID. I'm going to create a product ID, and then I'm going to have a date. These are date components. I just find it's much easier to handle it that way than having to parse like ISO strings or whatever. You can use date parts here. And then my aggregation comes here. I want to just count every time I see this product ID and date. I want to sum my quantity, and I want to sum the total price. And I want to output that into my sum product by date. So that's the extract part, that's the transform part, and then there's the load part. And that allows me to take the input data here that might be 10,000 records deep and come up with an output here that's maybe 5 records deep because I might have only sold 5 different products on that day. So that's an example of a small amount, like something that you might use if you don't have a ton of data and you can rely on, I don't need to worry about availability. I can just do this in process. I can run this maybe once a day at the end of the day, close the business, run this, and I can get my numbers. I don't have to worry about, chunking my data or batching my data. There's also the capability of using like an application process ETL. Now, this would be separate from your database provider like Mongo or SQL Server. In this case, it would be my application. I have a REST API that's written in .NET. Let's put together a sidecar application that, as I write to my operational data store, I want to also write to this other data store. One of the benefits of this is that you get like equivalent time series as an operational thing changes, I'm going to receive the updates in my aggregated data immediately because I'm writing it to both basically at the same time. But it does add an additional point of failure because if that sidecar process goes down, you're no longer getting data updates. There's also ways to handle multiple data sources. So let's say you have a series of microservices or you have reliance on external and vendor systems. So that's kind of like the generalized ETL process I talked about earlier. It's best to leverage a data lake to take a copy of the source data sets from their systems. Once you have your data in a data lake, you can process that data in place. You can slice and dice it however you want. And you can join it, build insights however you want that way without affecting the original data. Then you can run your various ETL processes, and then you can analyze it however you want. The main point is that you're trying to avoid affecting your core systems. There's this concept also with batch processing. Here's where we're getting into, I have potentially a lot of data. Let's say maybe not at the level of Amazon, but I am, let's say I do like 10% of Amazon sales. So I can't crunch through because I have a million transactions a day. I can't crunch through 30 days worth of effort in one because it's just going to take hours and hours of computation time. So the strategies there are to batch that. Typically track the last process and process data in batches that like, oh, give me every sale that's happened, but since the last time I ran this. The end of day inventory audit is an example of how I would use that. And then one of the final different ones that I'll talk about is stream processing. Now, in this one, you're getting as up to date as possible. If you're familiar with how Apache Kafka works, this is the equivalent of using like a K-table or K-stream for that. It provides near real-time aggregation if you have a mission-critical analytics process or some kind of auditing process that you need. And one of the drawbacks is that it's going to require tooling that's not typically included by most databases. In this, you're going to be, as data comes into my operational system, I need to be updating point in time my totals or my aggregation. And that's not necessarily possible with most database systems to do that. That's why they have triggering of, oh, I need to send an event, or I need to click a button and window it to recalculate that data and have it appear on someone else's screen. Okay, so I talked way too fast through all of this. Those are some very basic concepts of ETL. And so the last thing I have before I can open up for any questions we might have received is for further research. Apache has a lot of tools under the big data category if you're trying to do some more research into what happens, or like a Flink and Spark. Those are great for generalized aggregation. I have data from source system A, source system B. This one might be SQL Server, this one might be Mongo, and it has a somewhat like standardized query language that allows you to write it in an almost SQL compliant way to join that data together and aggregate it. There's also Azure has a very good description of the concepts of data lakes versus a data warehouse versus the hybrid, which they call the data lake house. Kind of an interesting term on their Azure site. I plugged Michael Perry's historical modeling. The concept of historical modeling is that I want to be able to, at any point in time in the future, go back and figure out how something happened in the past. So the idea of, don't make destructive changes, and capture the reasoning behind something, capture all the data you can, make it as granular and atomic as possible. That's all historical. That's the basic of historical modeling. And I mentioned the MongoDB aggregation pipeline. It's a very powerful tool if you happen to be using MongoDB. There's also, for Microsoft SQL Server, there's SQL Server Integration Services, SSIS. That one, it's very powerful. It's not nearly as user-friendly as the aggregation pipeline. It's a WYSIWYG editor. And then there's the AWS primer on ETL, which is also a really nice in-depth guide of what ETL is, and also the Amazon cloud offerings that support ETL. Okay, that was all I had. So hopefully there were some questions to be asked.